Hello and welcome to the introduction of our new Weihenstephan Standards domain WS Sweets for confectionery production lines. I'm Romy Ries, working at the Chair of Brewing and Beverage Technology at the Technical University of Munich, and I'm part of the Weihenstephan Standards team. In this video I will give you a short overview of the Weihenstephan Standards and explain our new WS Sweets OPC UA information model to you in more detail. In food and beverage production and packaging lines, you often find a wide range of different machines from different machine manufacturers. If you want to use higher level IT functionalities such as KPI calculation or batch and article tracing, you have of course to connect all these machines to the higher level IT system. As the machine manufacturers often have their own communication interfaces and provide machine or process data in different ways, the interfaces must be implemented individually. This is of course time-consuming and expensive. The same problem you have on the horizontal layer if you want to connect your machines to each other. Here, the Weihenstephan Standards helps you to get rid of the communication interface problems. A standardized interface simplifies the vertical line integration and M2M communication. The Weihenstephan Standards provide practice-relevant standardized data content for the machines of food and beverage industries and relies on the secure and easy-to-implement communication standard OPC UA. Furthermore, domain-specific recommendations for evaluation and reporting are provided to get an idea how the data gathered from a machine can be used. Let's take a closer look to the data content we defined within the Weihenstephan Standards. We defined a total of 150 different machines from the field of bottling and packaging, the meat processing, bakery, process area of breweries, and new also for machines of the confectionery industry. For each machine, we have defined a machine profile, or in WS Sweets, a complex information model that shows which data points are mandatory to be provided by the machine and which are optional. All these data points are also defined in detail by a specific browse name, a display name, a detailed description, further implementation details, the type definition, data type, and also the access permission rules. Let's see how we manage the communication via OPC UA. If we want to build a custom information model for a machine instance, we don't have to define these from scratch. We are using existing meta models and built-in information models of the OPC Foundation. On top of these, we are using other companion specifications such as PackML, machinery, or devices, for example, to use the PackML state model for our machines or the digital nameplate of the companion spec for devices. On top of this layer, we have defined our own OPC UA companion specifications for Weihenstephan Standards. In this specification, it is defined how a WS machine is structured and which data types are used. But in difference to other companion specifications, no specific machine type with data points are defined here. This gap is closed by our WS information models. In the version 10 of the Weihenstephan Standards, the data point machine assignment is done by an Excel-based permutation table tool, where you can see which data points must be provided or are optional for a certain machine class. The information model for a machine is here more or less a flat list of data points. In version 11, the information model is much more complex and all machines are provided via an OPC UA nodeset file. Before I continue with more details about the Weihenstephan Standard Suites, I will give you a short overview who founded and further developed the Weihenstephan Standards. Of course, it's not just us, the Technical University of Munich. Altogether, we have about 100 members in our WS industrial user group. These are engineering companies, as well as manufacturing industries, companies from the field of IT and automation, and also research institutes and associations. Together we have developed and defined the existing WS domains over the last 20 years. In our latest project, WS Sweets, we are now asked to focus on the confectionery industry and develop an interface standard based on the Weihenstephan Standards for transparent and efficient confectionery production. Once again, we had strong project partners on board who contributed their experience to the standard. As there is a big variety of products in the confectionery industry, as well as in the therefore required machines, the initial question was which machines should be considered in the Weihenstephan Standards Sweets project. Here, together with our project partners, we agreed to focus on 3 selected reference processes, as there are the production of chocolate tablets, the production of jelly products, the production of bars, and therefore we took into focus the 3 machines: molding plants, module plants, bar production lines, and for the production of the jelly and bar masses, also cooking plants. When we started with our project, the initial plan was to define a flat list of data points for all the individual machines, as we've done this in the existing Weihenstephan Standards domain. In the progress of our project, we had to realize that the machines could not be represented in this way, as they are much more modular and individually configured. I'll give you a short example. If you imagine a cooling station, you can define interesting data points for this cooling station or cooling tunnel. Let's say a state for this machine, a set temperature, actual temperature, and a set speed of a fan. If you now have even more or longer cooling tunnel with more than one zone, like 4 tempering zones, you have more data points to describe all the different zones. So in this example here, you have 2 set temperatures or 2 actual temperatures and 1 state which applies for the whole machine. Let's say normally a cooling tunnel has a maximum of 10 cooling zones. We therefore would define only data points for 10 different cooling zones, so temperature 1 until temperature 10. If a customer with a specialized product would need an even longer cooling tunnel, these additional data points for the cooling zone 11 and 12 would have to be defined individually by the vendor. So it's hard to sync all these possible configurations to the end, and therefore we decided to create a complex information model with components. So all the objects from the real world are also represented in the information model as objects with the corresponding data. In this case, a cooling zone is also represented by a cooling zone type with all the interesting data points underneath. So as you can see here, we have a cooling zone 1, and underneath the cooling zone you have the data for the set temperature and the actual temperature, and you have in one zone a single component which is a fan, and the set speed of the fan is assigned to the object fan. So this is the big difference between the version 10 of the Weihenstephan Standards and the version 11 for the WS Sweets domain. So in one case you have a flat list of data points, and now in the new version you have a really complex and component-based information model. So what we've done, or what's our result for WS Sweets? With WS Sweets we pursued 2 new approaches. This is the modeling of components. So a machine consists of component, and also components can consist of other components. And the second, we defined a complex OPC UA information model. Everything is stored in a node set file. So in this information model, we define types for WS Sweets machine. These are suitable for standalone machines, for example, a module plant. And here in these machine types, these machine types includes other components and also the interesting data point at machine level. And we have defined types for components. So these are suitable for non-standalone components, for example, for motors or tempering devices. These components includes also other components, or can include other components if necessary, and the data points which are relevant for the component. We also defined generic types and tried to harmonize these component types. For example, we've defined a generic WS component type with information which are relevant for almost all components, and derived all the specialized component types of these one WS component type. Since we didn't want to define each component from scratch, we tried to define types by derivation of other types, for example, a motor type, and derived an FC motor type. How this looks in detail, I'd like to show you now in our SiOME tool. Okay, let's have a closer look how our WS Sweets information model looks like in detail. We go to our OPC UA modeling tool. We are using SiOME, but you can use, of course, every other modeling tool instead. As you can see, I have already loaded all the required namespaces and loaded all, our WS Sweets information model. How to load all these companion specifications and also the WS Sweets information model can be found on our website and explained in another video. So let's see what we have defined. We go to the types, the object type, it's derived from the base object type, and scroll down to the WS types. If you highlight the namespace, you will see, it's easy to see all the types which are defined within the WS Sweets project and namespace. Let's see the machine type. This one is not highlighted because this is a definition in the companion spec OPC UA for Weihenstephan Standards. As I explained, we derived all our WS Sweets machine types from this WS machine type. Let's take a look, for example, for the molding line. What you can see here is now on this side here, the references, the derived members. So all objects here and variables are listed which are derived from the supertype. So all these informations are already included in the WS Sweets, in the WS machine type. This is, for example, these are the functional group folders for the states, for the measured values, the counters, batch and article tracing informations. So all these is already included in the supertype. You can see it here. And these counters already contain information. For example, consumption electricity, counter for good products and counter for total products. Or measured values, the actual machine speed. Furthermore, inside these WS Sweets molding plant type, other components are defined. You can see here a lot of other objects which are part of a molding plant or can be part of a molding plant. Here it is necessary to see the modeling rule of a certain component. There are objects which are mandatory. The box is ticked, the modeling rule is mandatory. For this example, this is a molding plant or a molding plant, and each molding plant has a demolding station, and this demolding station of the WS demolding station type is mandatory because every molding plant needs one demolding station. So this box is ticked. Other objects are optional. So here it's written mandatory, the box is not ticked. For example, here a cold stamping station from the WS cold stamping station type. So this can be included in a molding plant, but don't necessarily has to be there. The other part are the mandatory placeholder. For example, here you can see a depositor. The depositor is a mandatory placeholder. That means the box here is ticked and it's written mandatory placeholder. What does it mean? A molding plant without a depositor is not a molding plant. So each molding plant needs a depositor, and sometimes or quite often there are more than one depositor in one molding plant. This means it's a placeholder. This object depositor can be instantiated more than one time, but has to be there at least one time. Other things or other objects, for example here the ingredients insertion station is an optional placeholder. So here it's written mandatory placeholder, but the box isn't ticked, so that means it's an optional placeholder. It can be there, or it can be part of a molding plant. It don't has to be, and it can be also more than one ingredients insertion station inside one molding plant. So you can instantiate these multiple times. So these are the difference in the objects on the machine level. And of course, if you go deeper, you can already see the tree view or the how a molding plant is built. So you see the depositor. We said depositor is mandatory. The depositor itself is built from a depositor hopper, a dosing head in a dosing unit. The depositor hopper is built has other variables underneath. It's built from or can contain a tempering device and can contain an agitator, so it's optional. And all these are defined here in this hopper type, for example. Let's take another look to the component. So as I said, we defined a general component type with some basic informations which apply for all components. These are all optional. And from these component type, we derive the most of our smaller types. For example, here we found again the demolding station type. It is derived from the component type, brings already all the informations of the component type, and we have assigned more components or more variables on this level. For example, here we have a twister unit, there's a tapping unit inside. We can have a mold closing station or a mold opening station. And there are other mandatory variables as well. So this was our introduction into the WS Sweets OPC UA information model. If you'd like to get more information about the Weihenstephan Standards or see a video tutorial on how to create your own custom specific information model based on the OPC UA WS Sweets information model, just visit our website.